Welcome to Circuit Valley. I'm Gaurav. This video is going to be your ultimate guide for protocol decodation using an oscilloscope. This series of videos, we're going to decode every single protocol you can imagine. And in this video, I'm going to go absolute in depth of SPI. We're going to focus only on the SPI on this video to keep the video length reasonable, but we will cover every single detail. I have in front of you 3 oscilloscope setup. There are 3 different class of instrument. On the right side, you have RTB2004 from Rohde & Schwarz. This oscilloscope is 2.5 giga sample and 300 megahertz. It's quite modern oscilloscope, had quite a few modern features. In the middle, you have MSO 804A from Keysight. It is a 8 gigahertz and 20 giga sample per second oscilloscope. Quite a beast, a totally different class of instrument. Runs a Windows operating system and is opposed to RTB2004. Takes many minutes to boot. And in the bottom, you have my trusty old MDO3000, MDO3054, 500 megahertz, 2.5 giga sample per second oscilloscope. And we will try to decode every protocol you can imagine with all these 3 oscilloscopes, and we will take a look at them one by one. To help me generating all these signals, I'll be using a really interesting board. I'll show you in a minute how does the board looks and how does it behave. So let's take a look at the setup and we will show you. This is how all the props are connected. They are all connected to this green PCB in the middle. I'll show you in a second. RTB2004 has 4 channels and 16 channel digital. We'll be using few of the digital or maybe all of the analog channels. And my MSO 804A has digital and analog channels both. So we'll be using both. You can see there's one signal plotted there. There is a SPI coming from that board. And our MDO3000, it has also same 16 digital and 4 analog channels. So they all can decode quite a few protocols. RTB2004 a little bit more intuitive to use than other 2 oscilloscopes, but MDO3000 can decode quite a few more things, while this Keysight MSO 804A can literally decode everything you can imagine, even the USB 3 and PCI and everything else. This is the board, and every oscilloscope will be connecting to this guy. This board is MDO demo board from Tectonics, and when I bought my MDO3000, this board came with it. This board can generate quite a few type of signals. As I have pointed out in one of my previous video, it can generate I2C, SPI, MIPI, Flex, Ethernet, MIL, CAN, UART, RS-232, anomalies, counting signals, flip-flop edges, delayed signals, RF signals. Everything you can imagine this can generate, and we are going to take a look that how it's going to help us to be able to demonstrate and for the sake of learning how to set up a data decode on a modern oscilloscope. With the coverage of 3 different families of oscilloscope, I think it's going to be an appropriate coverage that we will be able to cover the whole spectrum and different type of oscilloscopes that are available on market. Modern oscilloscope, you will of course have RTB2004. For the relatively older oscilloscope, we will have this MDO3000, and for an enterprise class of oscilloscope, we will have MSO 804A. Few of the scenes which you will see, they will be recorded using the web view of the oscilloscope. RTB2004, most modern oscilloscope, had a really nice web view, while MSO 804A also have a web view and also supports VNC, so I can directly take the control of this oscilloscope from my PC. And the most amount of noise which you can hear in the background is coming from MSO 804A, MSO 804A, while Tectonics MDO3000 also have a web view. Its web view is not that intuitive. So just to take a closer look at the board, the slow signals start from here, and you see that there is a SS clock, DAC output, I2C clock, I2C data, and on the right side, maybe I'll remove some of the oscilloscope probe, there is a SPI clock, SPI slave select, SPI MOSI, and there are some digital signals. There is a fast flip-flop clock, fast flip-flop data, fast flip-flop, slow flip-flop clock, slow flip-flop data, slow flip-flop Q, fast flip-flop Q, 300 picosecond delay, and primary clock. There is a counting going on there, count with its clock, with the count data. I believe they are 7 bits or maybe 8 bits. There is a stepped edge, there is a MIL 1535, there is a 10 base T Ethernet, 100 base T Ethernet, and on this little header you again have all the signals combined. These are the DAC, raw DAC data, digital values, On this side you have high-speed signals, for example MIPI, or you also have USB LS, USB FS, and you also have USB HS. Probing a USB HS is going to be interesting. We will need two probes because I do not have any differential probe. So we'll learn about the probing as well, how to deal with a situation where you need differential probe and you don't have it. So our oscilloscope will help us. Only my 8 GHz oscilloscope can decode USB HS, and these normal USB speeds my MDO3000 can also decode. RTB2004 cannot decode USB at all. So what else do we have? We have flex connections, flex ray, RX and TX, and on this side you have fast edge, AM modulation, CAN, RX232, UART, LIN, frequent anomaly, rare anomaly, and SS pulse. You also have these signals available on you also have some of these signals available on this header, and there is also a 40 MHz clock, 2 nanosecond trigger, and 2 nanosecond pulse. This FPGA controls quite a bit of these signals. On this area you have RF section and some of the VCO, PLL, and some of the VCO, PLL, and ASK modulation stuff is available there. So right now I'll set up my oscilloscope to decode SPI, and I'll show you how to set up a signal and what to expect and what to watch out for. So let's start with RTB2004, and I'll remove my other oscilloscope for a second so that we get a little bit clear room here. Only the RTB2004 probes will be connected. So this digital probe, these three wires, channel number 0, channel number 2, and channel number 1 from RTB2004. These digital probe, these three wires, they connect to my RTB2004, and these three probes, they are also coming from RTB2004. This is my first channel of the oscilloscope, yellow, RTB2004. You can see on your screen right now, web view of the RTB2004, and this is supposed to be clock, and we see a clock-like activity there. I'll show you some advanced triggering as well, how to stabilize clock signal like that. And you see this is flickering sometime, and the reason for that is that our trigger is set such a way that it is supposed to look for a rising edge, and sometimes it's look for rising edge in wrong place, so it's not able to find the appropriate trigger for that. So we can easily fix that trigger should always be rock solid, so we'll try to find a solution there. Second channel is the green channel, third channel is the orange channel, and these three signals, they are visible on your screen. Let's separate them a bit. Maybe I'll decrease their height so that you can see them properly. And now they are separated. So on the third channel, or this brown channel, you see the data, and the green is going CS. Let me show you with the camera. So it's same thing which you saw on a web view. We are triggering on channel number 1, that's why it's flickering a bit, because there are multiple rising edges. And on the channel number 2, which is green, we see a CS pulse going down. CS pulse is generally what goes down for a longer period of time, and it stays low because CS is normally active low. It can be active high as well. And data is what have irregular length of pulses. You see data does not have a repetitive pattern like clock. So this is how you determine what is clock, what is CS, and what is a data. Data with the irregular pattern can sometimes naturally have a zero pattern or regular pattern as well, depending on what data you have. And but still it is very easy to recognize clock. CS is what goes down or goes to a change of the state for the whole period of the packet, and the data is which has irregular pulses, and clock is almost always regular pulses. First we will take a look at the trigger. What can we do with the trigger using RTB2004? So I'll use my mouse because this oscilloscope supports a mouse, and we can get rid of this counter, it's not needed. And first of all we need to zoom out a bit. So I'll change the time base to maybe 1 millisecond so that we can take a look at the packet. Okay, so now we are looking at the packet, and you see there is somewhere in between comes a big packet. Okay, we can also find that packet, and first of all we need to get a normal rock solid trigger, and we will see how do we get it, a basic rock solid trigger. My recommendation to always trigger on CS pulse or SS/select pulse. So I'll change the trigger to channel number 2, and now it's changed to channel number 2. And now we zoom in. Let's see our trigger gets stabilized. We are currently not at the current level, so increase the trigger level. We'll change the rising edge to falling edge so that we trigger at the beginning of the packet. Okay, now we have it. Now you can see it's already pretty stable. Okay, it's already pretty stable, so you can happily decode this signal and look at it, but still sometimes you see glitches. Okay, and these kind of glitches also you can be easily filter. One way of filtering these kind of glitches on any oscilloscope is going to be using a little bit advanced trigger other than edge trigger. Almost every oscilloscope which I know, which is modern enough, supports a pulse trigger. So we'll go in the trigger menu and we will try to set up a different trigger. This is the trigger menu, and instead of edge trigger we going to set the pulse trigger. Okay, so you must understand, first of all you need to find out the criteria, because pulse trigger, I'll show you, it has many options. For example, positive going pulse or negative going pulse. Do you want to trigger when pulse is greater than something? Do you want to trigger when pulse is less than some value? Do you want to trigger exact the same amount? This exact thing is somewhat dangerous or somewhat not that comfortable to use, because you need to specify a variation or a tolerance, because if you look for 50 microsecond pulse, it is not a mathematical comparison. So you can have any weird amount of pulse, and then you have to specify a tolerance. I rarely use exactly equal to. Sometimes I use not equal to with tolerance, and that is also pretty much helpful. Normally what I use is that if pulse is greater than something, so we'll set it to greater than something, and how much is greater than we will measure with our trigger pulse. We will measure with the cursor. This is the cursor, so you can set the cursor depending on your needs, and we will measure the CS going down. We will measure CS going down. How long does it stays down? So it stays around 40 microseconds down. You can see delta, and I'll trigger somewhere where it's greater than 50 microseconds. Okay, and let's see what happens. So right now trigger level is pretty low, so it will give you error-erroneous results. So we are triggering on positive going down pulse greater than 50, but you see this is a negative going down pulse, so I made a mistake. I'll go and change this thing to low going down. So now magically we are capturing that packet which was rarely getting repeated. So you see there is a big massive packet. For some reason I do not understand what does this packet say. We will soon decode it and we'll find out what does it say. So you see sometimes these small packets come, sometimes this big packet come, and we have a non-repeating or rarely repeating a packet available on the scope. Using a little bit advanced trigger of pulse trigger, we have found the packet. So this is just a tip, that advanced trigger or a little bit advanced trigger with pulse, you can easily decode or easily find the packet which you are interested in. Okay, so it was easy to define a criteria that greater than 50 microseconds. So it means that we are supposed to look for just a little bit larger package. So our trigger, oscilloscope trigger, is triggering on this packet because no negative going pulse which he found normally, because there is even oscilloscopes have dead time. We can talk about that later, but normally it founds this pulse after a long period of time. So he founds this first pulse. That's why you see trigger is right here, because time from this place to this place is greater than 50. This is how it founds it. So if you want to trigger it right here, then you can increase the time. I'll show you how to do that. Okay, let's go to trigger menu one more time. Maybe let's specify greater than 200 microseconds. Oh, maybe I entered some wrong value. 200 microseconds. Okay, and now you see, where are we triggering? We are triggering exactly at the end of that big fat packet. Okay, so we will try to decode it and we'll try to find out. This appears to be static data which is not changing. So we'll see what does the data says. So how do we set up a decode? We'll go to the bus menu somewhere down here. Oscilloscope also has button, but we are operating through web view, so we need to be limited in that. Okay, so now that we have a solid trigger on the signal, we'll set up a decode, and we will go to the protocol menu and we will set up a SPI decode. You can see there is two options available. One is SPI decode without CS, another is with CS. We need with CS because we have a CS available. If there is no CS available, I can also show you. You can decode SPI even without CS. Then you have to use this dead time as a CS, or oscilloscope can decode. There is no activity going on in this area, so then CS is inactive, then is activity again, CS is active again, there is CS not active again, and stuff like that. There are ways to mitigate that issue as well. So let's set the protocol to SPI with CS, and with this oscilloscope you have advantage you have this is exactly shows you which channel is which, and you can move around this window. Okay, so what you have to watch out, that we need to select the chip select for us is on channel number 2, clock is on channel number 1, and MOSI is on channel number 3. So this channel number 1, sorry, chip select is on channel number 2, clock is on channel number 1. Okay, so now we have it appropriate, and there are two things which are important. You have to watch out this diagram. So if you click somewhere else, this diagram changes, and many modern oscilloscopes have this feature that they will exactly show you what kind of waveform they are trying to decode, and these are the threshold. So you can also do find threshold, and it appears to be that it can automatically find threshold, and it did find automatically threshold. I generally do not do find threshold because this is somewhat broken of an option on most oscilloscopes. You should be better setting threshold yourself. So right now I do not know which kind of SPI it is. I'll show you. I'll zoom into the waveform while this window is open, and we will take a look what kind of waveform we are looking at. So you see our data here changes on falling edge, gets supposed to get sampled on rising edge, and it's pretty much obvious that data changes on falling edge, gets sampled on rising edge. So if I do this, there will be incorrect. If I do like that, it will be incorrect. Our CS polarity is low, and MOSI is normal active high, not active low. Okay, so this selection of the data is appropriate. Word size is 8-bit, and we have set up a decode bus. Let's cross it, enable this decode, and let's zoom out a bit so that we can see the data itself. Okay, there is some data available, and you see it is some kind of appears to be hexadecimal data, and it starts with B0, B1, B2, B3, 55AA, 00, 1, 2, 3, 4, 5, 6, 7, 8, 9, F. Okay, and let's see if it means something in other decoding. So we can protocol and display setup. You want to display hexadecimal or you want to display binary? Generally hexadecimal or ASCII is useful. So you see even in the ASCII it doesn't make any sense at all. You have this weird symbols. The people who designed this board, they intended to use it only for displaying of hexadecimal. They do not have any ASCII message encoded in there, so we are good with it. And one more feature I'll show you about this oscilloscope. If you zoom out a bit, okay, you see few packets, and you can go and say bus table. So this is our packet. I'm going to be stop capturing. I'll set it to single, and now it captured. And we will remove the meter so that you can see, and you see where is my marker, this packet, which you see this large packet, or where our beginning of the packet was. So this 03 is the beginning of our big packet. B0, B1, B2, B3, which you saw was the small packet after this start, and this 1, 2, 3, 4, 5, 6, 7, 8A is that big SPI packet. After that, what happens? They send 1136A 17 something something something. So this bus or this oscilloscope can show you exactly that what is the in-halt or what is the content of the bus itself. This may make sense once you have some kind of chip connected or chip talking to the device, which tells you exactly which bus or which tells you exactly what does these data means. Right now it's a demo board. It's just to show you that how the signals work, what kind of level they are, how to make sense out of them. So you have to rely on that. So now I'll maybe see if these data make any sense. So I'll go bus table one more time. I'll go configure, not configure, I'll say bus display, and I'll say instead of hexadecimal I'll say ASCII. Even they do not make any sense. Okay, so one more thing we can do, just in case we are doing some kind of reverse engineering, we can do configure and I'll say LSB first. Okay, and I'll do one more single captcha. Okay, and now this data has flipped, all of them has flipped. Okay, and now let's see if the bus decode shows us something, some better display, or it has some ASCII meaning to it. Okay, it still does not make any sense at all. So it was normal hexadecimal data which supposed to be look like a hexadecimal word with MSB first. You can choose LSB or MSB first. So there are many options available in normal modern oscilloscope when you try to decode something. Let's capture one more time. So this is how it looks. If you want to take a look at the oscilloscope view itself, so this is how this little oscilloscope shows the data. That's why I prefer the web view, because web view is a little bit larger screen and very comfortable to use. Now we will move to my MDO3000 and we will also try to record the web view of it so that you can see what are we looking at. And let's get started. Right now you can see that digital channels are connected to a DAC output or DAC input for that matter, and we will enable the channel number 1 and channel number 2 and channel number 3. They are different color scheme. Maybe we'll disable the digital channel. This oscilloscope is a little bit different to operate. It's pretty old. So we have our channels available to us, and we will connect the oscilloscope probes. It has a better quality probes than my MDO, than my RTB2004, and we will take a look at that. So this is how the web view of MDO3000 looks, and you can see it's somewhat clunky and these buttons and everything else is hard to operate. So we'll operate the oscilloscope using standard buttons, and you will only see the web view for the sake of ease of recording for me and not having any glitter or anything else. So I'll remove the probes from RTB2004 and we will connect my MDO3000 probe. These probes, they are better probe. They have spring loaded, better quality simply. I have been having this oscilloscope for quite some time. Channel number 1 is going to be connected to clock. Channel number 2, which is blue, is going to get connected to CS. Channel number 3, which is going to get connected to That's perfect. You can see on your screen many signals coming. I'll maybe show you. First of all, I need to adjust the voltage level for all of them so that they come into generate 2 volt per division is more than enough, but right now there are 3 signals on the screen, so I'll go to 5. Let's zoom in so that we can see what are we looking at. So we see exactly the same stuff, and this oscilloscope appears to be reacting faster than the RTB2004, because you can see this very rarely repeating pattern. It appears quite a few times on the screen. Okay, so this is also one thing to catch, that not every oscilloscope is same, and every oscilloscope does not react the same way. It may be just dependent on this feature or this, what do you call it, if you go to the acquisition menu, if you go to the trigger menu, then you have this hold off time set to, I believe it is the minimum value. I cannot set it to less than 20 nanoseconds.
so that's appropriate. If you set it to more than maybe a millisecond or something like that, you would not see your guy appearing all that much. So let's increase it just to show you. This is also one little quirk of this oscilloscope. You can enter the value, maybe enter 10 and milliseconds, or maybe I'll enter 100 milliseconds. Okay, now look, just by the increasing of hold off, our quirky signal does not appear on the screen all that much often. So this is one difference, and this kind of stuff you will not see on the web view itself. Okay, maybe I'll show you how does it look on web view, but hold off generally set to minimum is very recommended, and that's how world works. Web view is of this MDO3000 is very slow, and let's zoom in, and we need to set the trigger to channel number 2. Increase the level. This guy, and this scope is going total crazy on it, and we need to set the falling edge. Okay, I'll maybe just set it to directly to edge trigger, directly to a pulse trigger. Positive, not positive. I need a negative pulse, and I need look, it also have these different options. Suppose you choose equal to, so it has only one value and it does not have a tolerance. This is the thing you need to watch out for. If it does not have a tolerance, hitting a 8 nanosecond pulse exactly is going to be a challenging thing. Okay, and this oscilloscope has a really nice keypad, so you can just enter the value. Remember, we entered last time greater than 50 microseconds. This is an intuitive interface, and it looks really nice. Somehow we still do not see a stable trigger. Most likely this has to do with my trigger mode, and I need to do acquisition in most likely it has to do with my trigger mode, and I'm supposed to do normal mode, not hold off mode. Okay, because if you have the trigger in auto mode, so even if it doesn't find a trigger, it will automatically trigger, and this oscilloscope operating right now in very fast mode, so it will immediately find a trigger, it will immediately find a new waveform and display it. So you set it to normal, and now we see a stable trigger. Okay, it's very stable now. So now I'll show you how to set up a decode there. This oscilloscope has only 2 buses possible in one go. If you have MDO4000, you can decode a lot more buses, and right now the bus is set to parallel. We will change it to SPI. Okay, we will define input. The clock is on channel number 1, SS is on channel number 2, MSO on channel number 3. So everything is already set up, we don't need to do. MOSI is off. This oscilloscope, instead of having a dedicated option for SPI with and without CS, you can see framing is based on the CS or based on the ideal time. You can define the ideal time, I believe. This is the ideal time, how much bus has to become ideal before CS is being deactivated. So you can select if this is your CS deactivated, and also this thing is your CS deactivated. You set it, you measure it exactly, how much is this value, and you set it there as a deactivated value. If you want, I can zoom in a bit. So you measure exactly this thing, this period, and it will automatically calculate your CS is being deactivated. This oscilloscope is also not a basic oscilloscope. It can do a lot more stuff. Let's do one more time. We will set the trigger. That's perfectly fine. Threshold, look at this. Sometimes it doesn't find the threshold, and normally it's 2.8 volts for 5 volt logic. It's okay. And let's set it to 2. You can see also, it shows you, there's a line on your screen, you can look at it, and it shows you exactly where they're pointing the threshold. Okay, so if you set it to lower, the line says downward. Threshold you need to watch. Even when you are using the oscilloscope's MDO functionality, or even when you are using oscilloscope digital input functionality, you need to watch for the threshold. The threshold is appropriate value or not. So let's zoom in. This oscilloscope also has zoom feature, so we can exactly zoom in. And you remember last time we saw, this is the part of the waveform we are looking, and you remember we last time saw the packet start with V0, B1, B2, B3, and it does start with B0, B1, B2, B3. Okay, and maybe I'll set the bus to a little bit lower. It is somewhat overlapping right now. I'll select the bus. Now use the A knob. This oscilloscope has this multi-purpose knob, and you can do multiple things with it. Let's go zoom one more time. Now you can see it a little bit. You can see a little bit better. Same stuff, 1, 0, 2, 3, 4, 5, 6, 7, 8, 9, and up to F. And then these small packets, they start with 1, 1 and 1, 2 or stuff like that. This oscilloscope, I believe it also has bus display. In this oscilloscope has waveform. So this oscilloscope shows you one more feature which you generally may want to look for. Let's see if it is visible somewhere. We'll go in the top. So this oscilloscope shows you one thing which you do not normally find on a normal oscilloscope. After setting the threshold, you see the clock is being displayed twice. After setting the appropriate threshold, what did the oscilloscope understand of the clock? Okay, so it finds this clock. Maybe I'll disable the channel number 2 and channel number 3 so that we have less clutter on the display. So you see the clock is being displayed twice, and it's not a coincidence. It shows you exactly what did the logic analyzer or this protocol decoder understood as a digital waveform and what is trying to decode. So it will decode something like that. So if you have threshold problems, these kind of decode logic or decoded view of the bus is really handy. So you can say bus or bus with waveform and stuff like that. It can only show you hex or binary. It does not have SPI. And event table, same stuff. You can save the event table and analyze it later. And this oscilloscope is also, as I said, it's not a basic oscilloscope. It's also pretty advanced oscilloscope. It has many features which you can use. So we are done with this oscilloscope as well. So SPI, at least we have decoded with 2 oscilloscopes, and both have similar features. They say it differently. RTB2004 has one additional feature that it can display SPI, and it can exactly show you that which is which and configure the bus, and you can select and it shows you the waveform, and this guide doesn't show the waveform at all. Okay, so this is the menu. You configure the bus. It is positive going, negative going, active low, active high, active low, and stuff like that. Same stuff displayed in a different way on a different oscilloscope. So we got our scope set up, and you see that digital and analog, both of the channels are displaying same information. The clock is for digital connected on D2, and on analog channel connected on channel number 3. CS is connected on channel number 1, while on digital is connected to channel number 0. So now I'll go to the protocol decoder and show you how capable this instrument is. I'll set up a protocol decode. So we have the protocol SPI selected already, and we need a 3-wire, and data source is going to be channel number 3, or maybe not. This is the clock source. Data source is, let me look at it, channel number 2. Clock source is channel number 3, and chip select is channel number 1. So that is absolutely correct. So you can let it be, and you see that it doesn't allow us to invert the polarity of the data itself. It allows rising and falling edge of the clock selection, active low or active high chipset selection, and stuff like that. And I can do also auto setup, and you'll see this oscilloscope is smart enough to find everything what it need to find, and it will start decoding. It took quite a while, and now you see on the bottom side data is being decoded. I'll zoom out. Okay, you see that big packet still there, and maybe we'll set up a trigger accordingly. Let's go to the trigger menu. You remember we need a pulse width trigger, and pulse width greater than positive going, negative going pulse greater than 50 microseconds. Okay, so now we are having a solid trigger. Let's zoom in. This display is a little bit bigger, a little bit sharper, and you can see the display bus itself. It's showing data B0, B1, B2, B3, 55AA, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, F. So this is how this oscilloscope works perfectly, and it shows you exactly what it can decode. And let's look at the bus table itself. This is your view of the bus table. I don't know if you can increase it. Yes, you can increase it. This is the first packet which we capture generally, number 3, B0, B1, B2, B3, 55, 0, 1, 2, 3, 5, 7A, and it's 1, 2, 3, 4, 5, 6, 7, 28, something like that. The same stuff is being displayed. If you want, I can do a single capture. This is the single capture, and you exactly see the stuff which you have captured. If you want, you can zoom in and look at every single thing which you want to look at. So this is how we decode SPI with MSO S804A, and now let's move back to some other protocol. Now we will move to I2C, and we will do the same operation with all three oscilloscope. We will decode I2C. As I said, is going to be the ultimate guide. So we will decode every single protocol which every instrument can decode, and I'll show you how to set up and what are the pitfalls, how can you set up in between. I'll maybe show you how can set up an advanced trigger, and most likely you will not need to watch any other video. Once you watch this video, how to set up a trigger for a bus and how to decode a bus.